Well, thank you very much for the invitation to speak here and to open the special session. It looks like a great program. I think I'm going to learn a lot. So I'm very glad I'm giving the first talk, and then I can stop worrying about my talk and focus on what other people are saying. Um, Please do ask questions, either just unmute yourself and speak or in the chat. One of the things that's really hard about online talks is that they're not as interactive as a conference should be. And so I really want to encourage people to step forward and to ask questions. So what I'm talking about today is the symmetric algebra of the Virasoro algebra and its Poisson structure. And mostly, actually, what I'm going to be talking about is functions on the Virasoro algebra, and then applications to the Poisson structure of the symmetric algebra. All of this is joint work with Alexei Petukov, and almost all the results I'm talking about today are in a preprint that we put on the archive last month. So let me introduce, first of all, the main characters of the talk. So these are the Lie algebras. First of all, the Witt algebra, which is vector fields, algebraic vector fields on the punctured complex line. So in other words, it's Laurent polynomials in T times the operator del, which is my notation for d by dt. Then the bracket just comes from commuting these, say, inside the Weil algebra, and here's the formula for it. So this is a Lie algebra, and it also has a very interesting central extension, the Virasoro algebra, which looks, of course, like the Witt algebra plus a central element z, and then the bracket is there's a cocycle that tells you what scalar multiple of z you have in, and otherwise it looks like the Witt bracket. So the Virasoro is one of these objects that kind of shows up all over the place in mathematics. It's important in physics, it's important in representation theory, not just representations of Virasoro, but also if you're looking at another Lie algebra or another algebraic structure, you'll often find Virasoro sort of creeping in. It's one of these things that shows up a lot, and so it's important to understand it. And I should say that it's the unique central extension of the Witt up to isomorphism. So I'm a ring theorist. So every time I see a problem about Lie algebras, I say, okay, well, let me think about the associated rings, the universal enveloping algebra of the Lie algebra. So these are, of course, Hopf algebras for this workshop. And what they give you a way to translate the representation theory of Lie algebra into a question about representations of an associative algebra. Right. So what's known about the ring theory of these enveloping algebras? In general, enveloping algebras of infinite dimensional Lie algebras are quite mysterious, unlike the finite dimensional case, which is at this point very well studied and very well understood. So first of all, these are very big rings. They're the same, they look like polynomials in infinitely many variables with a non-commutative structure. And one way to see how big they are is that a basis for the Witt algebra looks like generalized partitions, non-decreasing sequences of integers. So this is saying that the growth of the enveloping algebra as an algebra grows like partitions of n, which grows very, very fast, certainly faster than any polynomial. They're very non-commutative. They're more non-commutative than almost any ring you can think of. It surjects onto every Weil algebra. And the big question about enveloping algebras of infinite dimensional Lie algebras is there an infinite dimensional Lie algebra that has a left and right Noetherian enveloping algebra? And then you can ask it more generally about connected Hopf algebras of infinite GK dimension. So the Witt algebra is the first Lie algebra for which this question was answered where the answer wasn't easy. So this is a theorem of myself and Chelsea Walton, who I'm glad to see is here. We proved in 2013. Neither of these enveloping algebras is left or right Noetherian. And I've got my MSRI mug from the semester at MSRI where we proved this theorem. So this is a question that was out there for a long time. Whether the enveloping algebra of the Witt was Noetherian was asked in a paper of Small and Dean in the early 90s. And one of the surprising things about this theorem is actually the proof was sort of sitting right there in plain sight all along. So what's the proof? Well, there's a ring homomorphism. Well, there's a map from the Witt algebra to the localized Weil algebra, which I'll write kind of abusing notation as polynomials in T inverse and this operator del. I mean, this is just the obvious map since the Witt algebra was constructed as a vector, as a subalgebra of that under the bracket. So this is the obvious map from the Witt algebra to the localized Weil algebra. And it turns out that the kernel of this map is our infinitely generated left and infinitely generated right ideal. So it's the obvious thing you might want to look at to see if the ring's Noetherian. But one of the interesting things about these enveloping algebras is that they seem to have a very sparse two-sided structure. So an example of this is that the kernel of this map pi naught, this infinitely generated one-sided ideal, actually as a two-sided ideal, its principal, it's generated by just a single element. Further evidence that these have very few two-sided ideals is that two-sided ideals in the enveloping algebra of the Witt algebra, say, are very, very big. This is a ring that has infinite GK dimensions, sub-exponential growth, but any proper factor of it has polynomial growth. So what this says, right, is that ideals in this enveloping algebra are so large that they take this huge algebra and knock it down to look like a polynomial ring in finitely many variables. So the growth here, say a little bit, is this GK dimension. How you calculate it, right, is you take a finite dimensional vector subspace and you look at its powers and measure how fast that grows as a function of n. And for a commutative domain, this growth, this GK dimension just measures the transcendence degree of its field of fractions. And as I said, the enveloping algebra, the Witt algebra, goes like partition numbers, so faster than any polynomial. So this theorem, which Natalia Eudu and I proved a couple of years ago, it has a slight generalization that actually works for any central quotient of the enveloping algebra of the Virasoro algebra. So if I factor out z minus lambda for any scalar lambda, again, this has this just infinite GK dimension. Any proper factor has polynomial growth. So again, the Virasoro algebra, the enveloping algebra of the Virasoro, also seems to have very, very few two-sided ideals. So this suggests the one-sided structure of these enveloping algebras is going to be impossible to get a handle on because of the non-Noetherianity. But the two-sided structure, it seems like it's tractable. So this has been, in some sense, one of my main research goals for the past few years, to understand this two-sided ideal structure of these enveloping algebras. So two questions that you can ask. First of all, do the enveloping algebras, do these have the ACC, the ascending chain condition on two-sided ideals? It seems plausible, right? I mean, here's this very, very big one-sided ideal that was not only finitely generated, but actually generated by one element. And then when you're thinking about ideals in a non-commutative ring, you always want to ask, what are the primitive ideals? What are the annihilators of simple representations? So these are probably the two questions about this ideal structure that we most want to ask. So here I say, I can't answer them. These are too hard. So as one usually does in research talks, I'm going to set up my goal, then I'm going to say it's too hard, then I'm going to move the goalposts and change the question and make it easier so that I can answer it. So instead of thinking about the enveloping algebras, let's think about the symmetric algebras of these Lie algebras. So as rings, these look like polynomial rings in a basis for the Lie algebra, so just polynomials in countably many variables. But they also have this Poisson structure. There's this bracket, which I'll write in curly braces, which is induced from the Lie bracket on G. So how do these how does this Poisson structure work? Well, it's a Lie bracket on the symmetric algebra such that it's a derivation in acting on any one of the inputs. And I'm interested in Poisson ideals in the symmetric algebra, where a Poisson ideal is an ideal which is not only of the ring, but also a Lie ideal under this curly braces Poisson bracket. And my notation for this is going to be triangle sub P for Poisson ideals, since we're going to have lots of them in this talk. Why do I care about the symmetric algebra if I'm really interested in the enveloping algebra? Well, the enveloping algebra has a filtration. In fact, it's the co-radical filtration of it as a Hopf algebra, where the associated graded of it is the symmetric algebra. So what that says is that Poisson structures in the symmetric algebra, you expect them to be sort of shadows of structures in the enveloping algebra. And an example of this is that if I've got a two-sided ideal in the enveloping algebra, then I can take the associated graded of it and I get a Poisson ideal in the symmetric algebra. So I had my original goal to understand two-sided ideals of the enveloping algebra of these Lie algebras. Let's change it. I want to understand Poisson ideals of the symmetric algebras. So we can move our questions over to the symmetric algebra side. For example, we can ask, do these symmetric algebras satisfy the ascending chain condition on Poisson ideals? And if we could prove that, it would imply that the enveloping algebras had ACC on two-sided ideals. Again, there's some strong evidence in support of this. For example, there's a Poisson version of this theorem of myself and Ayudu that says that Poisson ideals of the symmetric algebra of Virasoro are big. Right? If I take any proper Poisson factor of one of these central quotients, then I have polynomial growth. And there's also, they also both have the ascending chain condition on radical Poisson ideals. So this is, I mean, I have to say I can't answer this question, but I think there's strong circumstantial evidence that it's likely to be true. Okay, so far what I've done is I've asked questions and said I can't answer them. Let's start asking some questions which I can answer. So what about primitive ideals? What does that look like when we move to the Poisson side? So I want to find the Poisson primitive ideals of the symmetric algebra of Virasoro. So let me tell you what those are. Well, given a Lie algebra G and a function on G that is an element of the dual space, this gives you a maximal ideal of the symmetric algebra because the function chi defines a ring homomorphism from the symmetric algebra to the ground field. The Poisson core of this function or of this maximal ideal, which I'll write core of chi, is the maximal Poisson ideal contained in the maximal ideal corresponding to chi. So breaking that down a second, the maximal ideal corresponding to chi is certainly an ideal in the symmetric algebra, but it's probably not a Poisson ideal. So here we're looking for the biggest Poisson ideal contained inside this maximal ideal. And we say a Poisson ideal is Poisson primitive if it is the Poisson core of one of these functions. Why do I care about these? Well, first of all, we think these should be the shadows of primitive ideals in the enveloping algebras, in the enveloping algebra. For finite dimensional Lie algebras, this is something called the orbit method, and it's well established through a long series of theorems. Furthermore, if I were in the finite dimensional setting and I had an adjoint group, then the Poisson core of chi would be precisely the defining ideal of the coadjoint orbit of chi. So these Poisson cores have something to do with coadjoint orbits, which is, of course, a long studied topic in representation theory. Right. So I want to find out the Poisson primitive ideals of Virasoro. Let's start with Poisson primitive ideals of the symmetric algebra of the VIT, which is clearly the first step along working towards Virasoro. So this splits into two subproblems. First of all, which functions have a non-trivial Poisson core? And then secondly, can we describe the Poisson core explicitly for functions with a non-trivial Poisson core? So we can answer both of these questions. We do in our paper, but in this talk, I'm just going to focus on the first question, which are the interesting functions with a non-trivial Poisson core. So let's have an example. Let's take a triple of scalars, x alpha beta, and not too many of them 0. And I'm going to use them to define a function chi x alpha beta on the Witt algebra. And it sends f del to basically a linear combination of f of x and f prime of x. So I evaluate f and its derivative at this point x, combine them together. So this is a perfectly fine function on the Witt algebra. The one thing I want you to notice about this function is it vanishes by construction on all multiples of t minus x squared inside Witt. Just as notation, I'm going to need this all multiples of a function g a lot. So let's call w of g all the multiples of g inside the Witt algebra. So let's get another ring. This is the localized Poisson-Weil algebra, which has a Poisson bracket induced by defining the Poisson bracket of t and y to be 1. I'm going to define a function p beta from the symmetric algebra of the Witt to this localized Poisson-Weil algebra, where I send f del to fy plus beta f prime. So two things to notice about this. First of all, the kernel of this map is contained in the maximal ideal associated to chi x alpha beta. One way to see this is that chi x alpha beta clearly factors through p beta, right? Because the only thing I need to compute chi x alpha beta is evaluating f and f prime at the same point, right? The other thing to notice, this is a computation which I'm not going to do right now, but you can check, is this is a Poisson map. It preserves the Poisson bracket. So what this says is that the kernel of p beta is a Poisson ideal. So we know at this point that this function chi x alpha beta has a non-trivial Poisson core. And in fact, its Poisson core is precisely the kernel of p beta. And furthermore, these kernels are all of the Poisson primes in the symmetric algebra of the Witt algebra with sort of codimension 2. So I'm going to generalize this example. So for me, a local function on W is a linear combination of taking derivatives at points. So it's something that looks like chi of x alpha beta, except maybe higher order derivatives, maybe more than 1 point. What it's doing is it's looking at local behavior at the function f for finitely many points. And the first main theorem in our paper is that for functions on W, there's 4 equivalent conditions. First of all, the function's local. Second of all, it has a non-trivial Poisson core. Thirdly, the isotropy subalgebra has finite codimension. I'll come back to that. And fourthly, this function vanishes on one of these W of h's, the multiples of a function h. So notice that we've seen that 1, 2, and 4 hold for the function chi x alpha beta. So what about condition 3? So what is this isotropy subalgebra? Well, any Lie algebra G acts on the dual space. You first bracket 2 elements together and then apply the function, the function you're thinking about to get a new function. You can look at this as defining an alternating bilinear form on the Lie algebra, rewriting it slightly. And the isotropy subalgebra of chi, right? Well, on the one hand, it's everything in the Lie algebra that sends chi to 0, as you should expect. But also when you work through the definitions, it's the kernel of this bilinear form, the stuff that evaluates to 0 against anything using this bilinear form. So in the example chi, I'm not going to compute the isotropy subalgebra full out, but notice that it contains all the multiples of t minus x cubed, right? Because when I bracket a multiple of t minus x cubed with anything, I get a multiple of t minus x squared. And we saw that this function chi vanished on all multiples of t minus x squared. So again, here we've got the isotropy subalgebra having finite codimension, which is the third equivalent condition in our theorem. So I'm not going to say much about the proof of this theorem, but I did want to mention the proof of 2 implies 3. So this is a non-trivial Poisson core says the isotropy subalgebra has finite codimension. It turns out to be a general fact that for any Lie algebra and any function on the Lie algebra, an upper bound for the codimension of the isotropy subalgebra is given by the transcendence degree of the ring you get where you factor out the Poisson core. It turns out to be one of these nice proofs where it just comes down to evaluating the right determinant. A lot of mathematics seems to do that. So suppose I've got a function that has a non-trivial Poisson core, a function on W that has a non-trivial Poisson core, right? So then the Ayudu-Sierra theorem says that I factor it out, I've got polynomial growth. In other words, its transcendence degree is finite. So therefore, the codimension of the isotropy subalgebra is also finite. I'm not going to do the rest of the proof. Let me instead move on to talking about consequences for the symmetric algebra. Well, first of all, subalgebra is a finite codimension. This doesn't look like it has much to do with Poisson ideals, but it does. So it turns out that, this is just restating the theorem, and it turns out a corollary of this is that any subalgebra of finite codimension needs to contain some W of F. How do you see this? It's actually quite quick and quite nice. Let's look at a basis of W mod G star, which I think of as a subspace of W star. Then each of these functions has to have a finite codimension isotropy subalgebra, or the rank of this bilinear form has to be finite, which means all these functions are local by the theorem. So by another condition of the theorem, they all vanish on some W of HI. So this means that if I look at W of the product of HIs, right, then all of the chi's vanish on that. But by construction, G is precisely the subspace of W where all of the chi's vanish. So I've just shown you that G contains W of something. You also get from this that any finite codimension subalgebra of Virasoro needs to contain Z, actually in its derived subalgebra, which was previously only known for codimension 1 subalgebras. So this is a quick application of knowing the image of G is a finite codimension subalgebra of W. It therefore contains some W of F. You lift that back up to Virasoro and do some computations, and you get that Z is in the derived subalgebra. So this is all well and good, but it doesn't seem to have much to do with Poisson ideals. Finally, let's do something with Poisson ideals. A function on Virasoro with a non-trivial Poisson core, which means here not equal to Z minus chi of Z, has to vanish on Z and therefore give a local function on Virasoro mod Z, which is the Witt algebra. How do we see this? Well, the Ayudu-Sierra theorem says if the core is non-trivial, I've got polynomial growth when I factor it out. Therefore, the isotropy subalgebra has finite codimension. Therefore, Z is contained in the derived subalgebra of the isotropy subalgebra. But by definition, chi vanishes on, well, and vanishes on Vir chi bracketed with anything, let alone Vir chi bracketed with Vir chi. So this says chi of Z has to be 0. As an immediate corollary, we get that the Z minus lambda, where lambda is non-zero, are maximal Poisson ideals of the symmetric algebra. So why not? Why? Well, suppose not, then there's another ideal. Therefore, this function has a non-trivial Poisson core, and that forces the scalar lambda to be 0. I'm going through this quickly because I know I'm running short on time. So I haven't discussed the second question, describing the Poisson core, at all. But not only can we answer it, but we have many consequences. So just as one example, the maximal Poisson ideals of the symmetric algebra of Virasoro, we've actually seen them all. There are these Z minus lambdas where lambda is non-zero. They're the kernels of these functions P beta, now thought of as a function from symmetric algebra of Virasoro. And of course, the augmentation ideal is a maximal Poisson ideal. And basically any question you want to ask about Poisson ideals of this symmetric algebra of Virasoro, we can answer using this, using largely the technology of this first theorem, the equivalent conditions for local functions. So, okay, but I care about enveloping algebras. So to end the talk, I'm just going to ask a bunch of questions about the enveloping algebra. Yeah. So is there a version of the orbit method, right? Once we know about Poisson primitives of the symmetric algebra of Virasoro, which are supposed to be coadjoint orbits, does this tell us about primitive ideals of the enveloping algebra? Is U of Vir factored by Z minus lambda simple, where lambda is not zero? Does the enveloping algebra of Virasoro have ACC on two-sided ideals? So these are all good questions, but again, I'm coming back to, I can't answer any of them at this point, even though I know a great deal about the symmetric algebra. So I'll stop here. Thank you very much.
Thank you so much for this great talk, Susan. I will stop the recording for questions now, so people feel